All right, I'm going to continue with our last video. It stopped on me prematurely, so I'm just going to continue where we were. And you can see the screen is as I left it, where we had just finished this part here with the final answer down here at the bottom right here. So we just finished that. So that's the number of ways to return the hats so that no one of them is in the correct order, because I took the total arrangements n factorial and subtracted from them the number with one or more out of order, or in order, sorry, one or more in order. The first one here is with one in order, the second with all the ways with two or more in order, etc. So a derangement is just one of these things where you have an arrangement of ordered items, distinct items, is an arrangement of the items that leaves no single item in the original place, and the number of ways to derange n distinct items, these are distinct items, is denoted by d sub n. And by the result we have above, if I can go ahead and put this in here as a formula, then using this formula up here but removing the negative signs would be n factorial minus n choose 1 times n minus 1 factorial plus n choose 2 times n minus 2 factorial, etc. So this will be now minus plus all the way to the n, where we have a minus 1 to the n, because this was an n minus 1, and that'll be times n choose n, like so. All right, so what I want to do with this is actually do something kind of clever with it, and that is recognize that there is some cancellation we can do here, because the n choose 1 is n factorial over 1 factorial n minus 1 factorial, and then we have times n minus 1 factorial, and those will cancel. And this is n factorial over 2 factorial, n minus 2 factorial, and those also cancel. And this persists, minus plus dot 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 plus minus 1 to the n, and this is n factorial over n factorial times 0 factorial, but I'm not going to put the 0 factorial there. And the reason I want to do that, I'm going to cross out this right here, is because I don't want to write this with an n factorial pulled all out in front. If I pull an n factorial out of this, let me go ahead and write that n factorial and the minus here and the plus here, etc. Then I have a 1 from the first term, a minus 1 from the second term, right? This one has a just an n factorial there. I pull it out, I leave a minus 1, but I want to write it over 1 factorial. I know that looks a little crazy, but I do, because this one becomes 1 over 2 factorial, and minus plus, and the same pattern persists all the way to the n, where here I have a minus 1 to the n, pull out an n factorial, and I'm left with a 1 over n factorial. So this is 1 factorial, 2 factorial. This one in here that I didn't write down is a 1 over 3 factorial, etc. All of those are there. And so that's our an expression that is pretty nice and easy to remember for d sub n. There's one other thing I want to do here, and that is I want to say the probability of a derangement if n objects are randomly ordered is dn over n factorial, and using our expression for dn above, as we have it there, the dn up here, the n factorial cancels, leaving 1 over 0 factorial, yeah, I'm going to write it that way, minus 1 over 1 factorial, plus 1 over 2 factorial, etc., minus plus, dot, 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 plus minus 1 to the n over n factorial. And in fact, that number is approximately equal to, lo and behold, the number e to the minus 1 power. It's an approximation, but it's a very good approximation. And so I will stop it here, and we'll do examples in class on this crazy thing of derangements.